Hello everyone and welcome back to another video. In today's episode we're going to be discussing the periodic table, specifically trends of the periodic table, and ones that you need to be aware of moving forward. So before we move into trends, let's briefly discuss history of the periodic table. So in 1869, the Russian chemist Dmitry Mendeleev published the first version of the periodic table of the elements. It showed the ordering of the known elements according to atomic weight, and it revealed a pattern of periodically recurring physical and chemical properties. We now know, however, that the periodic table is not arranged in order of atomic weight, but in order of atomic number, which is the number of protons an element contains. Using this new revised table, many properties of elements that had not yet been discovered could be predicted, because the periodic table creates a visual representation of the periodic law, which briefly states that the chemical and physical properties of the elements are dependent in a periodic way upon their atomic numbers, which is denoted by Z, and it is the amount of protons an element contains. So we know that the modern periodic table arranges the elements into periods across, which are the rows, and groups, or columns, which are up and down. There's 7 periods representing the principal quantum numbers n equals 1 through n equals 7, right here, for the S and P block elements. Each period is filled sequentially, and each element in a given period has one more proton and one more electron, the element to its left. And this is obviously referring to the elements in their neutral state. And the groups, or the columns, contain elements that have the same electronic configuration in their valence shell, which is their outermost shell. And this is hence why groups, the columns, elements of the same group, contain similar chemical properties, such as the halogens, or any other group for that matter. So let's briefly run through this before we hop into the trends. Metals are obviously found on the left and in the middle of the periodic table, and below with the lanthanides and actinides. That's just for space reasons. And then on the right, we have the nonmetals and the metalloids. The metalloids obviously form the staircase, highlighted in this light blue color, and nonmetals are found over here to the right. So metals are malleable, ductile, lustrous, and electropositive, whereas nonmetals have high ionization energies, high electron affinities, high electronegativities, and they're poor conductors of electricity. And the metalloids, they share some properties with metals and others with nonmetals. For instance, metalloids make good semiconductors due to their partial conductivity of electricity. So this brings us to our very first trend of the periodic table, electron affinity. I've drawn the red arrow across the periodic table displaying its trend. It increases from the bottom left to the top right. So what is electron affinity? Well, electron affinity is the energy dissipated by a gaseous species when it gains an electron. You can think of it as an opposite sort of concept than ionization energy. Electron affinity is an exothermic process, and therefore its delta H has a negative sign, but it's actually positive. The positive is net. The next trend is ionization energy. It also increases from the bottom left to the top right. Ionization energy is denoted by IE. It also goes by ionization potential. It's the energy required to remove an electron from a gaseous species. From a chemical standpoint, we know that this must require an input of heat, therefore this is an endothermic process. And this is going to be an example of how you would display such an ionization energy, such as a first ionization energy. You do Mg, it'd be in the gas phase. Goes to Mg plus gas plus an electron. So that would be the first ionization energy. The first ionization energy will always be smaller than the second, which will always be smaller than the third, and so on. One thing to take note about ionization energy is that if losing a certain number of electrons gives an element a noble gas-like electron configuration, then removing a subsequent electron will cost more energy. Another important trend of the periodic table is atomic radius, which is different than ionic radii, which I'll briefly discuss following this. Atomic radius of an element is equal to 1/2 of the distance between the centers of two atoms of an element that are briefly in contact with each other. This distance is akin to a diameter. So as you move across a period, as the proton increases, the electron increases, the shell remains constant, therefore the atomic radius will shrink. So picture it this way. We know that this is the first principal energy level. This is the second, third. So these are all shells that are being added to this atom. So down here, that's going to have 7 shells, theoretically, and it's going to be the largest element. Whereas helium, up in the top right, has 2 protons, 1 shell, and 2 electrons that are going to be highly attracted to that positive nucleus. Ionic radii is a little bit different. We go over this in general chemistry a lot. Anions that acquire an extra electron are going to be larger than a neutral atom, and cations that lose an electron are subsequently going to be smaller than the neutral atom. This is because more protons, less electrons, those electrons are going to be tugged tighter into the positive nucleus, whereas if you gain electrons, it's going to add more space to the atom. Another trend that I found interesting to add into here is lattice energy. Lattice energy is defined as the energy required to separate a mole of an ionic solid into its gaseous ions. It cannot be measured empirically, but it can be calculated using electrostatics or estimated using a Born-Haber cycle. Now, obviously, with positive and negative charges, the two main factors that contribute to the magnitude of lattice energy are charge and radius of the bonded ions. Here's just an example of an ionic solid and its lattice energy being released into its constituent ions. So therefore, we know that this isn't going to be an exothermic reaction, and heat is released into its surroundings. So the last trend that is highly important, moving through general chemistry, organic chemistry, and into biochemistry and all your other chemistry courses, is electronegativity. Electronegativity is a measure of the attractive force that an atom will exert on an electron in a chemical bond. The greater the electronegativity of an atom, the more it attracts electrons within a bond. This trend increases from the bottom left to the top right. Here's a display of the periodic table in accordance to the Pauling electronegativity scale. Here we see more specifically the actual values of the atoms. We know that fluorine, oxygen, and nitrogen, and even chlorine are some of the highest, most electronegative atoms. So to summarize, grab a pen and paper and write this chart down. From going from left to right, atomic radius decreases, ionization, electron affinity, and electronegativity increase. And going from right to left, atomic radius increases, ionization energy, electronegativity, and electron affinity all decrease. So that's important to note. Make sure to write that down. These are some of the best trends to keep memorized as you move forward in your chemistry courses. I hope this helped. We'll see you in the next video. Thank you for watching.